Hi, in this lesson, we will learn how to calculate forces involved within a cable that is subjected to a series of point loads. My name is Jurapot Jikrawacharadet. This course is a part of a program in International Program in Civil Engineering at King Mongkut University of Technology, Thonburi. I am happy that you are here with us, and let's begin the lesson. First, let's look at an example on how we have to analyze cable in civil engineering. What you see here is Ramanai bridge. It is a type of bridge that we call a cable stay bridge, meaning it actually supported by cables as well as some other structure at the same time. Another example is Rama 8 bridge. These are different type of cable stay bridge, but nevertheless, it's involving calculating the tension within the cable to support the bridge itself. These are typical schematic of cable stay bridges. There are different ways to define it, but similar in this approach. There are some anchor on both sides of the banks, also some foundation if you need be to support the cable in the middle. Right, there's a deck roadway or something that the road can run on, and then we have the main cable that is in tend to be kind of inclined angle or in a parabola shape, and then we have the vertical or sometimes called suspension cable that actually transfer the load from the deck or the roadway up to the main cable, and then the main cable transfer it to the column. You see the high column there, and then down on the tower, and then down to the foundations, and of course to the anchor block and on the idle banks. In this course, we are not going through up to the point where we actually analyze the total cable stay bridges, though. Right? We just learn the basic, and maybe if we are interested, we can pursue that in the higher level of our education. Right? So as a basis for it, we look at the cable, how it's reacting if we put in serial point loads onto it, and then we look at how it will behave under distributed load. And of course, there's when it's really long and it's really big, then the self weight also has some influence on how it behaves. However, in this course, we'll focus on these two areas. Right? This lecture, we will look at the serial point loads, and the next lecture, we'll look at how it takes the distributed load in general. Well, since the cable was subject to the point loads, there are not much theory behind it. We already know how the cable actually behaves from the Madhyam 6 high school. So we just extend it, right? And the whole thing is presumably the load is so heavy that the cable doesn't curve. It just it behaves like a straight line, or presumably could be considered a straight line. So we'll begin this lesson by example, right, on how we actually analyze the whole system of cable. In this picture here, there are two supports at point A and point D, right? And usually, as we have a pin joint at point B and point C, right? And then, as I said, the cable is assumed to be straight line. So these are the type of problem we will be solving, right? So basically, in these questions, we will solve for all reactions at, of course, at point A and point D, AN and D dot, of course. And then we will have to find all the tension within the cable, the height H, right, to maintain the system to be in equilibrium, of course. Before we actually start with the calculation, let's ask ourselves first, can we solve this using equilibrium? So basically we are trying to figure out whether we have enough equation to solve all the unknowns we want to solve, right? So let's start from analyzing the unknowns, right? And then follow it up by the equations, right? In the example, the unknowns are obvious. We have 4 reactions, 2 pin support at point A and 2 at pin support at point D dot. So basically that's 4. We also have 3 main cables, A to B, B to C, and C to D, right? 3 axial forces inside the cable, right? Tension basically. And then we miss out one dimension that the question doesn't give us, that is the H, the height H, right? Well, the problem is that if we don't know the H, we don't know the angle, right? The angle that the inclined angle of CD, meaning we cannot take component into X and Y direction of the tension CD, right? So that's become a problem. So basically, not a problem, it's become an unknown that we need to know before we can solve everything. Right? So basically, in total, we have 8 unknowns. Now, how do we analyze equations in this kind of system? The same with thrusters, right? This one here, we look at the joint, and we know that in this case, we have 4 joints, A, B, C, and D, and each joint in 2D, this is a point, joints are points, so you have already sigma fx, summation of force in the x direction, summation of the y direction, right? Therefore, 2 equations per joint, right? So which means totally you have 8 equations. You have 8 unknowns, you have 8 equations, so you can solve it, right? And this type of structure, when we have enough equilibrium equations, I emphasize the word equilibrium equations, right, equal to the total unknowns, we will call it a statically determinate structure, meaning all forces, internal and external, can be determined using static alone, is equilibrium alone, right? However, as long as this structure is stable as well. Okay. Well, let's look at the Fibonacci diagram, because our problem doesn't end just because we have enough equations. This is a more complex situations, right? So let's say if we draw the whole Fibonacci diagram, you see that from A to D dot, then we will have 4 unknowns, right? This is a body, so we have summation of forces in the x and in the y direction. We have summation of moment, so we have 3 equations. So basically, we have 4 unknowns. We have 3 equations. Obviously, we cannot solve all 4 forces using one Fibonacci diagram. So there are many ways to do it. I would choose the one that easiest to explain. So if I draw, say, equilibrium Fibonacci diagram of point A, joint A, right? So now we have 3 unknowns, right? AX, AY, and tension in the cable AB. But we know that we have only 2 equations per joint, right? So it seems like we still stuck, but not really, no. Because if we count these 2 pictures together, then because RAX and RAY are the same RAX and RAY on both picture, so in fact we have a total of 5 unknowns: RAX, RAY, tension in AB, and then RDY, RDX, right? So 5, in fact, 5 unknown, 5 equations. So if we use 2 Fibonacci diagram, then we can solve all the 5 unknowns. Okay, so we will begin to use that method then. Okay, here the 2 Fibonacci diagrams together. I will start from the right hand side first, okay, because there's some hope that we can solve something, right? I will start from taking moment at point D dot, right, which then in this case I can find RAY straight away. If I have RAY, then in the y direction, again, still on the right-hand side Fibonacci diagram from A to D, right? I can do sigma Fy, right? Because then I have only RDY left in the y direction. So there we go. So now I have AY, RDY, right? So now X, there's no point doing it because I have 2 unknowns, I have 1 equation. So I move on to the left-hand side Fibonacci diagram, right? And then I will look at sigma Fy first because I already know RAY, right? There we go. So if I do sigma Fy, then I can find the tension. And if I know the tension in between A and B, then I can use sigma Fx to calculate RAX. Once I know RAX, then I switch back to the right-hand side picture and do sigma Fx for the right-hand side picture, and then I can find RDX, right? So now, as I said, because altogether we have in fact 5 unknowns and we have 5 equations, 2 together we can solve it, right? So now here's what we have, right? We have all reactions done. We have 1 tension already between A and B, right? So let's move on to the next step, right? We can actually start doing point B boy, or we can go and do D dot, right? Depending on what we want to do, right? So I will move on to point D dot just because I'm more familiar with this type. So I go to D dot, draw out a Fibonacci diagram. As I already said, Because we don't know h, right? So we don't have the total complete picture of the triangle. So that angle theta that we need to actually take component of TCD is unknown. So these two unknowns, right? One is the force tension in the CD cable and the angle it made to, in this case, I draw it as the minus x direction, right? Theta. Nevertheless, we have two equations, we have two unknown that should be able to solve it, right? Sigma fx then, start in with the equation, right? So I name it the equation 6. Then sigma fy, I get another equation, and equation 7. Right. If you start to see the pattern, now we have on one equation we have the sine theta, on the other side we have cosine theta. Right. I will solve first for the angle of theta. So I put 6, 7 up and then divide it by 6. TCD disappear, of course. It's the same. Sine over cosine become tangent, or well, you call it tan usually, but yeah, the word is actually tangent, right? So once we have the value of the tangent, when we use arctangent to find the angle theta, right? Now we have the theta. I will explain later how we're going to use it, but in this case, I will use take advantage of, I know that sine square plus cosine square is equal to 1. So I power up equation 7 and equation 6, combine them together. Then, of course, as I said, on the left-hand side, I pull out TCD square out of the bracket. Then in bracket, I have sine square plus cosine square equal to 1, right? And then I can solve for TCD, tension in this cable CD, of course, right? So let's update for what we have. Right. So this is what we have. We have all reactions. We have tension in A, B. We also have tension in C and D. Right. We also have the angle that we already calculate, theta. Right. So if we look at the triangle here, right, then we can calculate h, right? Because again, we use the relationship between angle and the side. We know only one side. We know the angle. Therefore, we can find other sides if we want. In this case, h equal to 1.824 meters, right? Right, and which I update in the picture. Now, because we're going to move on to find cables BC, then we need to know the angle, right? So we work on the information we already have. I'll draw a triangle on the left-hand side between BC, right? Work out the gap between the 2 meters and the 1.824, right? And then I can find the angle. This time I call it alpha, right? This is the one BC to make it to x-axis. Now again, we can go to point B, we can go to point C, the same, right? I move on to joint B first. Okay, so this is the angle, right? The angle alpha I already calculated, so I know what it is, right? And I already know the angle of AB, right? So just a free body on point B, simple enough. Now if I do sigma fx, then I can find TBC. Now notice that we have equation left, right? We haven't done sigma fy yet. That's one thing. And we haven't actually looked at joint C at all, right? Usually we have these leftover equations, and we can use it to actually check whether we did the right equation or not. So in this case, I would do it, right? So I do sigma fy, and then I sum up 0 equal to 0. That's good, right? Joint C is the same. I know all the forces, all the angles already, right? So what we do now is to check sigma fx, then we get 0 equal to 0. Good. Sigma fy, then we get 0 equal to 0 as well. So it's just kind of like proof that well, it's not really proof, but it's kind of a check that the whole system is in equilibrium. So hopefully we didn't do any miscalculation in between. Well, these three equations for checking, you don't have extra math for them. So unless you really do it, so don't bother writing in. Right? It's a waste of time. But I would recommend you to really check it. Right? Okay. So let's summarize all the problem we have done. So we find all reactions. We also find all the tensions and the height, as the question asks us to do. Right. So we are happy now. Well, as I said, we are happy. So let's be happy. Well, it's done for today, and I hope to see you again in the next lecture. Oh, by the way, I left out some extra example. It's a little bit more complex, right? I will leave the note in the LEB2 as well. Have fun then. I'll see you soon. Bye bye.